to the Faculty Academic Staff Forum at the University of Wisconsin-Eau Claire. My name is Erica Benson. I'm the Executive Director of the Office of Research and Sponsored Programs, and I am delighted to introduce today's speaker. Dr. Patricia Cleary is a professor in the Department of Chemistry and Biochemistry, and she will be talking to us about her studies of air quality near Lake Michigan. So looking forward to that. But before I turn things over to Dr. Cleary, I want you all to know, and those of you online too, that we will have time for discussion after the talk. So be thinking of your questions and comments. And I will ask you, Dr. Cleary, as we get questions from the audience, if you could repeat them for the benefit of our online viewers, that would be great.
Okay.
Appreciated.
Wonderful.
And please join me in giving a warm welcome to Dr. Cleary.
This is a picture that we took in the field from a drone. That was really fun. So the two people on the outside are my collaborators from Purdue. And then I've got 4 of my students who are in the field that year: Kelly Korber, Autumn Civilet, Akatorti, and Kevin Wangen. And there's a bunch of other people that I have used the work of in this talk. And so I'm acknowledging them here. So the issue that I care about, or that I've been studying, is air quality around Lake Michigan. And so this is a figure from, a paper from 2022 that has the counties that are designated as in non-attainment of federal ozone standards in either pink or blue, and when they've overlapped, they're purple. So blue is from 2008 standards, pink is 2015 standards. And then there's all these dots that represent where there are EPA measurement sites. And you can see that obviously Chicago is a problem, but we have counties along Lake Michigan, both on the Wisconsin side and the Michigan side, that are in non-attainment of federal ozone standards. And even if you kind of zoom this out, this is a NOAA, an EPA-based map of like where the poor air quality locations are across the country. And we zoom that out, we can see other Great Lakes also have these problems. And we sometimes think that it's also just the orientation of Lake Michigan that means that you get a lot of surrounding counties. But we care that people aren't breathing in high levels of ozone. There's some esoteric ways that we can calculate that. If you want me to go through them, I can. But for now, I'm going to talk about the research that we have been doing at Chewocki Prairie. So you notice that that's one of these really red dots in this image. So it's one of the county-based sites that is one that triggers Kenosha County as being in non-attainment, and it's one of the highest design values for the state of Wisconsin. So in order to think about ozone, we have to think about like why it gets high in areas around Lake Michigan or anywhere where we have ozone as a problem where people breathe it in. So I'll call that the lower atmosphere or the troposphere. This is the mechanism to build up ozone in the troposphere. So we need some precursors. So we need volatile organic compounds and we need nitrogen oxides, so NO and NO2. During the day, sunlight will produce this hydroxy radical, this OH, a really small amount, but this is the thing that reacts with a lot of things in the atmosphere. And so the hydroxy radical will react with volatile organic compounds. So what do I mean when I say that? That's like acetone, like your fingernail polish remover, your gasoline, the stuff you smell when you open up a paint can, that stuff that is you can smell, that's volatile organics. And a lot of that comes from industrial activity, but some of it also comes from trees and plants as well. So there's only a certain amount that we can control for emissions of volatile organics. And then nitrogen oxides come from, there are natural sources of natural oxides, but what we see in industrial areas is inefficient fossil fuel combustion as our source of NOx. So there's this cycle where we initiate a reaction with volatile organics that will often add oxygen very quickly, and then the conversion of NO to NO2 through the reaction with what I'll call the peroxy radical. This is the way that where once we've made NO2 in this direct mechanism, the NO2 will photolize, react with another O2 and make ozone. And there's, a secondary reaction where this can sort of degrade and then produce a HO2 to do a secondary. So it's like for every one OH and VOC, we should be making 2 ozones. And just in general, this is the most chemistry I'm going to show you in my whole talk. We need some precursors. We need volatile organics and we need NOx. We need to have sunlight to initiate these reactions or sunlight to photolize NO2. And then we need to have a stable atmosphere. So the atmosphere mixes by the fact that the sun hits the surface of the planet, and then the surface of the planet heats up the atmosphere, and then the atmosphere gets cooler and cooler as you go up in altitude. Or, you can also think of it as an adiabatic expansion of a gas if you want to think like a peak chemist. But we've got warmer air near the surface, colder air aloft. And because of that, the air has buoyancy. So the buoyancy usually makes the pollutants that we emit as surface level beings that we are, they mix out. But if the atmosphere has something that we call an inversion, it traps it in, it makes a little reaction chamber. And so the lake also creates a localized meteorology that is that reaction chamber. So it's called the lake breeze effect. I mean, so it's sort of described by how you feel the lake breeze as a person on land. This GOES imagery shows the development and extent of a marine air incursion over land. And so what you're seeing in that video is when warm air that contains water rises, we can make cumulus clouds. It doesn't always happen, but it can happen. If the air is not rising, you don't get the clouds. And so that's where you have a localized high pressure system over the water. And so it's sort of pushing down and not letting warm air rise. So that's an example of this reaction chamber. And so the reason why it's high pressure is because the surface waters are colder than the surface of a land. There's a difference in heat capacity between water and land. So if you've ever tried to swim in Lake Michigan, especially on the Wisconsin side, it's cold, right? So the air above it is also cold, and that air it prevents mixing above it. And so we'll see the effects of that in the summertime. So the first indication that I could do something with drones came about from the Lake Michigan ozone study in 2017. And this is data that came from a manned aircraft that flew around Chewauquee Prairie, offshore of Milwaukee and up to Sheboygan, and they did all of these spirals to sort of capture the lower atmosphere. And they're going between close to the surface of the lake. I think that these pilots were getting, I think this is meters above sea level, not even meters above ground level. So they were getting like within 50 meters of the water on this aircraft, which is pretty intense. And they saw really high ozone. So like the color map, red is high ozone. That offshore from Milwaukee, they saw high ozone, but it's at very, very low altitudes. And so this is indicating that this inversion layer over Lake Michigan is really, really thin. And so we're condensing our container for doing our chemistry into a really, really small layer above the lake. And so I saw this and I said, well, flying drones, we can do that safer than flying a manned aircraft really low toward the water. We can fly it from, the ground up, and we're connecting domains. We can connect between, a point measurement at a ground site to maybe what can be observed more easily from a manned aircraft. So with that, I got my first NSF grant to do a series of experiments, which began in 2020. Very fun. As me and Joe Hupy, we were not allowed to bring students into the field that year, but we were outside. He said that there's no traffic driving through Chicago as he came up from Purdue in June of 2020. And we flew out at Chewauquee Prairie. So let's see, this is the location that I'm taking a picture of, sort of facing this direction. The air monitoring site is this little thing here. And so we flew this copter to different altitudes and hovered at different altitudes with an ozone measurement and IMET sensor, which can measure temperature, relative humidity, and pressure. So we mounted, this is the personal ozone monitor that would measure ozone, and then my IMET sensor, and then, I would do a calibration before a series of flights. This was, I'll show you in the data, but like we had one drone, we had two people. It would take us 3 flights to get 3 or 4 flights or change of batteries to get one full profile from 0 to 120 meters. So we sampled between June, so June 8th and 9th, and then 15th through the 19th. And the aim was to go out when ozone was a problem. So here's the 8th and the 9th. This is the Rackham's forecast model from Brad Pierce at University of Wisconsin. And so he was like my forecasting guy, and I would ask him like, is it gonna be bad? And he said, yes, go out in the field. So that's 8th and 9th. Here's the 15th through the 19th. We had some really nasty days, and I feel like a bad person when I'm like, oh, ozone's gonna be terrible. Let's get in the field. But that's what we did. And there was observable lake breezes. So if you look at this image, you see a bunch of clouds on the left, and you see no clouds on the right. And so that's that transition between there being moist air rising and creating clouds, and then buoyancy suppression or a lake breeze. So what do we see for these? This is that week where ozone was high. I'm graphing my data. On the y-axis is altitude, so I'm breaking all the rules of like the independent axis is on the x-axis. It's on the y-axis because we're human beings and our head points up, and it's easy to think about the atmosphere going up. So altitude versus potential temperature. The way that we should view potential temperature in these graphs is that when potential temperature is vertical, you have a well-mixed atmosphere. When it's diverting to the right, that means it's inversion. And then overlaid on these, the colors are telling you when ozone is high. So this day, ozone is high sort of below an area of inversion, below area of inversion, below area or right at the inversion. And, we took measurements in the morning and in the afternoon, and that was a lot of work because we would do 4 different battery changes, and we would go back to the hotel, plug in all of the drone batteries and let them charge for several hours, and then get back out and do a series of flights in the afternoon. So, but for 2 people, this much data was a lot of work to acquire. But I'll show you that like things got better as we went, as I did more of this. So in 2021, we acquired another collaboration partner with the University of Colorado. They brought out this Raven platform, which is has some more sophisticated measurements for meteorological measurements, and that was really fun. You can launch it from the top of their car with a pneumatic like a trigger, like it flies. They have to like a slingshot, but it's like a piston, right? And we flew a different kind of multi-rotor, but similar setup. And there was also a Doppler LiDAR instrument, so that works by sending light, bouncing laser light off of particles in the atmosphere, and then analyzing it spectroscopically through the Doppler effect to understand the movement of the particles, and you assume that the particles are moving with the wind, so you get an idea of winds. The Raven was able to fly for 2 hours straight, so that fixed wing that looks like an airplane. For some of our measurements, just flew over land, and then some measurements it flew over water and land, and then we would do our similar flights for the drones, for the rotors to measure ozone next to the air monitoring station. And so here's here's a complicated picture of some of the combined measurements from that, from another paper. So the top images from left to right are a bunch of flights. So now we've got like flights almost every hour or 2 hours. So we were starting to pick up our pace. We had better batteries on the multi-rotor copter. And so the colored dots are the multi-rotor copter measuring ozone. And then the orange lines are the temperature profiles that were measured by the Raven. And the Raven had FAA approval to fly up to 500 meters above ground level. We didn't do that for the rotor, but this is still potential temperature. So anytime we see like something super vertical, we'd say, okay, that's a well-mixed atmosphere. And then we start to get this divergent and then to vertical. So here's my layer that is showing the lake breeze or marine air incursion. And the thing that we started to notice is that there's an area where it seems to be well mixed and then inversion, a capping inversion. And then in June, we were still observing where it starts to be well mixed above there. So the arrows are also showing the wind direction as measured by the Raven. So you can see a change in the wind direction, like winds coming from the southeast to be going from the southwest as you go up in altitude. And as we measure ozone, we're seeing ozone high in areas closer to where there is inversion than at the surface where it's well mixed. And there's the bottom figure is it's more meteorological esoteria that if you want to talk about a bulk precision number we can, but I don't really feel like it. So what we can see from over water to over land comparisons, that's what I've got here. The blue lines are showing Raven profiles over water, and then the orange is Raven profiles over land, and all of the drone measurements are over land. The dotted lines are an indicator of maximum buoyancy suppression, or maybe where you would think of like the most sort of divergent from a vertical line that we would get in our potential temperature vertical profile. And what we also see is that for most of these, the blue line is below the red line. So over water, we have a shallower depth, like vertical depth of inversion. And then as that air comes on land, we have some kind of buoyancy, some kind of mixing. It's probably just hitting a bunch of trees and stirring up all of this, a certain amount of eddies and stuff like that change our vertical profiles as we come on land. And so that was really interesting to show that the inversion depth is changing as you move these air masses over land. So by 2022, we decided on a acronym, WISCO-DISCO. This is Wisconsin's dynamic influence of shoreline circulations on ozone. We were back in the field. Now we flew two similar rotor aircraft, one over land, one over water, and we were going to look at both the ozone and the vertical profiles of the temperature, humidity, pressure to understand how they can differ in less than a kilometer distance from where we were flying them. We're still going out to Chewauquee Prairie. So this time, similar location to where the air monitoring site is for where we did our overland profiles. But then over water, we would go over to Phil Sandard Park. We would launch from the street, and then we would try to get a little bit out over the lake so that we weren't super close to the shoreline. And we would, through walkie-talkies, we would try to do a vertical profile at the same time, multiple times a day. So this is a picture from the overland drone. And so you can see the air monitoring site. We had some tents that we would sit under in between flights to get out of the sun. And then this is the Phil Sanders Park where we would launch and try to fly out there. In 2022, we captured a bunch of lake breeze events or at least marine incursion events. And in this figure, I've got it in gray of when I would indicate, okay, there's marine air influencing this site. So how do I know that it's marine air? One way to do it is I look at the wind direction, and the wind direction shifts between coming from the west to coming from the east. So east would be in any eastern component is 0 to 180. And then this would be any western component, right? And these nice sawtooth jumps is really like a big wind shift. You also see a corresponding drop in temperature, right? So, you know, a normal kind of rise and fall of temperature during a day might kind of look more normal to us who don't live by a lake. But if you have a lake incursion, you get like temperatures rise in the morning and all of a sudden the winds shift, and then it's more stable, or it's just lower in temperature, and then they may shift back later in the day. And there were 2 days that had high ozone, which were associated with lake breezes as well. So this is the 20th of June, and this one is the 24th of June. So we were out there, there's lake breeze, there were high ozone conditions. Great, well, something to sample. I also worked with the folk, again, Brad Pierce's group at University of Wisconsin-Madison to do some modeling for me on those 2 days we saw high ozone. And, you know, they show like a stark contrast between overwater and overland conditions. So a lot of doing this work is motivating, how do we model the ozone, or how do the models need to change to get the ozone concentrations better in this environment? And it really has to do with scale. It's costly to start to think about layers in the atmosphere that are on the order of tens of meters instead of hundreds of meters. But at this location where there's, you know, high density populations and poor air quality, we say the model requires that you have to have a higher resolution in this area to capture these effects. That's like the end goal. Not that I'm making the model, but I'm indicating to the modelers what they could be doing. So we did some flights. On the left side is overland, on the right side is over water, and we will see different profiles if we fly over land and over water. We might see where inversion is, or inversion looks strange. This is still potential temperature versus altitude. I've put the dots on to be ozone. I'll kind of click through these. Sometimes at very different depths of where inversion can be found. And then we get to spaces where, I don't know, the data looks like that it's really high ozone in the areas of almost constant inversion over water, but we've got that mixing depth over land. And you know, later on, we're starting to see higher ozone in that inversion layer. Sometimes they look pretty similar. But let's see, this is one of the days where it got really hot. This is the 24th. And so we still see, like, late in the day, right, 3, 4 o'clock in the afternoon, over land, we've got ozone that's, you know, cooking up close to 100 ppb, and then really high in this, you know, 90 to 120 20 meters above ground level. And that just the depth of where inversion starts is a little bit lower over water. The campaign that we did in 2023 was like a conglomeration of a lot of different field campaigns. And so a bunch of field campaigns had different acronyms, and then they made the Ages Plus to be all the acronyms of, like, an acronym of acronyms. It's kind of esoteric. It's like Aroma and Gotham and whatever. But what they did was NOAA and NASA had manned aircraft that would fly either out of California and sample mostly the west and over water out the west, or we had a set of the part of the campaign that was out of Dayton, and then they would choose day to day, like, okay, the skies look clear in the Chicago area, we're going to Chicago today, or we're going to Toronto today, or we're going to New York today. And my group was a part of this very large, like hundreds of scientists participated in this field campaign, and there were many aircraft in the air, a lot of agencies and universities involved with that. And this is the year that we revived the OPSIS instrument, which is a differential optical absorption spectrometer. And if that doesn't make a lot of sense to you, that's okay. If you've ever used a spectrometer that has a path length that's like a little cell and you just like, I see that's pink, and you put it in, you get a number. Well, this is one where the path length has to be 600 meters long for us to measure stuff in the atmosphere. So that instrument was mounted to two buildings across the harbor from each other in downtown Kenosha. And then we did more measurements with drones down at Shiwaukee Prairie. So that year there was an ozone LiDAR instrument, which is very cool. So similar to using lasers and pointing them up into the atmosphere and looking for them to reflect back down, you can do the same thing with lasers and actually get the composition of ozone or the concentration of ozone as a function of altitude. But when you do that, when you have to bounce a laser up and then it has to come back, you have the speed of light limits what areas of the atmosphere you can sample. So you have to send the light and it has to come back. So really close to the device, you can't measure it because you don't know if it's coming or going. So there's what they call like a dead zone for LiDAR. So they were flying their own drones next to the LiDAR instrument, and then I was flying my drone out over the water. So we could get over water and over land comparisons. And then they've got a really beautiful LiDAR instrument that gave really beautiful data from that. So this is some of the data from the OPSIS instrument, the differential optical absorption measurement. And like, this is just like one way to say, did it measure something that we think is reasonable? So the black data is ozone as measured down in Shiwaukee Prairie, which is pretty pristine. There's not a lot of other pollutants being emitted in that area. And then the blue is OPSIS ozone only. And the red is OPSIS odd oxygen, which is the sum of ozone plus NO2. And the reason why we use that is that if there's a bunch of cars driving around, they're emitting NO, and that quickly reacts with ozone to make NO2. So atmospheric chemists call this like the titration effect of ozone. But so if we calculate odd oxygen, and that's the red, we're getting closer to what they see out at Shiwaukee Prairie during the day. So these really high ozone events seem to agree better if we pay attention in the inner city of Kenosha to odd oxygen. But then at night, they both agree because the titration effect isn't really as apparent. So like, I think the OPSIS data is reasonable. It seems that we're sampling ozone in a way that seems regional, and we have some metric for the influence of localized NOx onto those measurements. And this is a series of flights that we would do. This is now the most data intensive field campaign that I've done, where we were flying once an hour, sometimes for 12 hours a day. That was exhausting. And I got heat exhaustion. It was terrible. The pollution was bad. It was hot, but you know, we got it. So the top data is ozone as a function of altitude. So this is just time of day. This is like, here's another flight, here's another flight, here's another flight. There were times when like a storm would come through and we would, you know, not fly. And then the bottom are temperature profiles. And so if you see a colder temperature underneath a hotter temperature, here's a inversion happening. And then we've got a bunch of inversion here. We got high ozone. So I can pick out some of these more inverted days, like cold air, lake breeze, high ozone. We're still working on analyzing that data. I know it's been a year, but it takes a long time. So yeah, with that, like that's a survey of the data, that what we've acquired. My current National Science Foundation grant is to build an NO2 instrument to fly on the drone. So then I can get ozone and NO2, and then I can do more odd oxygen measurements and do a bunch of field campaigns and actually buy my own drones. So all of these experiments that I've done were with the Purdue drones, and Purdue is going to help me buy and develop my UAS training plan for students here, it was nice to have somebody else do that. If it all becomes me, that's a lot of work to make sure that we're following the FAA guidelines and doing everything safely and dealing with very high power lithium ion batteries and not starting fires and stuff like that. So with that, I've left time for questions. So thank you for your attention. Thank you to all of my funding sources. And yeah, I'll entertain questions now. Oh, well, wildfire smoke was a huge issue during Aegis Plus because it was high, and there's a lot of people doing studies on those days. Like, so these days here were some smoky days, and it's confounding. And there were hundreds of measurements, on aircraft and all of that. So to get high ozone, typically near Chewauquee Prairie, usually we have to have a high pressure system over the Ohio Valley, and it creates a circulation pattern of the winds so that the winds are coming from the south. And that allows there not to be too much strong east-west wind. And also the high pressure system makes there be like not a lot of clouds. So if there were just like thunderstorms coming through, we're not going to get high ozone. So I do this sort of tailored, like I want to go out there when the air pollution is bad. And so I only go when the conditions seem to be right. But you can have measurements that like are continuous, like the ground site monitoring sites. But what I want to do is understand that mixing depth and of the lake breeze. And you don't get the lake breeze if the winds are coming out of the west. Yes.
So, in my years out in Oregon, we would experience warnings about inversion layers all the time. Because of being trapped.
Yep.
And I thought, gee, why? That'd be a great little sandbox for this type of study. But then I think Sarah might have pointed out why that isn't a good site. When you brought up your map of where these studies are happening, I didn't see the Willamette map.
Well, I didn't zoom out.
Okay.
I mean, all of the Central Valley of California is a huge inversion, and they have some of the worst air pollution.
Right.
Yeah, Salt Lake City, same. Yep.
We're trying to isolate what exactly is causing this, right? So we have around Lake Michigan, we have all of our centers of industry studying the coastline. Now I'm understanding why Aldridge parked its main chemical manufacturing campuses there. But yeah, seeing how this is kind of ideal with that isolation of the open water.
So it's UV absorption, and there's an issue that water also absorbs in the UV. And the larger instruments usually have 2 optical cells, and they scrub the ozone out of one of them, and then they do a whole layer measurement out of the other, and then your measurement is the difference between the two. And the personal ozone monitor works the same way, but it does it in series. So it does 5 seconds of scrubbed air, 5 seconds of whole air, and then you do a subtraction. So it's really fussy and it's really noisy. $5,000, maybe $6,000 now.
And what's your NO2 instrument?
This is really fun. So it's a cavity enhanced LED instrument. So I'm like, this is like, I have built when I was in grad school an NO2 instrument that did laser induced fluorescence with a Harriet cell, and now it's going to be very similar parabolic mirrors, but it's just going to be an LED that's just kind of smacking in there and bouncing around, however. And you calibrate it kind of like a DOAS. So it's going on and off some spectral features to look at that. Yes.
What is your control? Like if you're saying like, this is what good clean air looks like. If you're always going out on the worst things, like how do you?
Well, I think what I'm trying to do is take measurements well of the phenomena at the scale that it exists within, right? So the control, like I have a bunch of flights where ozone isn't piling up, right? But I still see inversion. And so it's ephemera. That's the problem with this kind of work. You're just trying to get a snapshot of what's happening in the atmosphere at a given point in time. And then you can test that. I guess some of the stuff, some of these lines that I have in one of these graphs, let's see. This one. So there's the NAM, the National Atmospheric Meteorological Model, right? Has a mixing depth that's a part of a meteorological model. And so I could say, well, that's these lines that I have in here, and I can compare my measurements to what the model predicts. And if sometimes the model's saying that the inversion depth is at 200 meters above ground level, and I'm really showing that most of the inversion is happening under 100 meters, right? Everything is parameterized from the meteorological model from, historic meteorological data sets. And now I'm just comparing that and also adding on there like an ozone measurement. Great question. It's usually comparison with models that you're using. Yes.
So I know you've thought about this a lot and shared at this point for a long time. There's a lot of factors that go into this. So this is a good example, this right here.
Yeah.
So on one hand, there's clearly, it's possible there's a mixing, right? There's
Yeah.
the mixing thing that you're talking about, but at the same time, there's this diurnal effect
Yes.
too of the
Yes.
buildup of NOx
Yes.
in the atmosphere, especially
Yes.
in an urban area.
Yes.
And also, but there's also the diurnal mixing phenomenon, right?
Yeah.
So we have a lower inversion layer in the
Yeah.
evenings and in the.
Yeah.
So how do you tease out this multi-factor analysis?
Well,
So
again,
you're saying it's about the mixing as opposed to NO2 or even temperature.
well,
right?
like it's a series of field studies where I add another layer of complexity, right? So here's like two times in a day, and you obviously can see a diurnal profile in there. But then when we get to 12 times a day, you can actually see this development at times of inversion.
Oh,
Let me see, where's one like, is this one a good one? Like colder, hotter, above cold, like you can sort of see a variance in that inversion depth. And this one is like, here you've got warm air sitting underneath colder air, like so, right? You start to see that how things grow and change if you sample enough in time. It's a harder experiment to do that than twice a day. And we've kind of figured out how to do that. And then the next thing, how do we test for NO2? Well, you got to put an NO2 instrument on there. So
there's a big convolution between mixing depth and time of day as well, right? Or is
in inversion, it's slightly different, right? I'm measuring inversion. I'm not measuring mixing depth and planetary boundary layer like collab, whatever you call that, from the morning, right? That's not what I'm looking at. I'm looking at mesoscale meteorology. But you're right. I mean, I think most of what I'm trying to do is sample the atmosphere and some important key constructs so that I'm indicating to modelers, like, what's the scale that you need to think about? Where is all the ozone? Is it just at the surface? Is it sitting above the surface and then it hits some trees and buildings and stuff like that and starts to mix down? Because then if they had like a surface friction model, it might explain neighborhood scale differences, but you have to have a higher resolution model.
But I think we're all starting to get it now that this is also why I'm just thinking back to Dieter's question about controls. Well, what if we perform the same experiment, let's say 500 miles offshore in the Pacific, right, where you have no building structures to cause mixing, obviously no trees, nothing like that. That's not relevant because there's no inversion layer to concentrate.
Right. And so my perspective is different than the meteorologist. The meteorologists just want to capture consistent measurements all the time because they have to model the atmosphere. If you want such a thing to know about the weather, like they want as much coverage as possible, but it's still ephemera. You still have to say, like, we can only send up like, so many balloons a day or whatever that is. Yeah.
But isn't the other difference that in some sense you're doing observational science?
Yeah.
Somehow phenomenologically different than experimental science, because there is no such thing as a control
Yes,
theory.
yes, right, yes, yes. That's the problem.